Since late December, the Hunga Tonga Hunga Haipai volcano has seen a lot of activity in a series of pretty big eruptions. On the 14th of January, it was spotted erupting again by local scientists. This seemingly huge eruption shot ash 20 kilometers into the atmosphere, creating a pillar which stretched high above their view. But this is all about perspective. The impressive sight from a ground view only appeared like a tiny little pillar from space. The next day, this happened. This eruption, seen by both the GOES West and Himawari 8 geostationary satellites, showed the biggest explosion captured on camera, perhaps ever. Initial reports state this could dwarf even the biggest man-made nuclear explosion, and it's not hard to see why. Just look at how big the ash cloud is. If we overlay it over Europe, we can see that it covers an impressive surface area. Sorry, Luxembourg. Not visible in the satellite images, but detected with radio wave listening instruments, more than 200,000 lightning flashes were counted in the plume. Volcanic lightning is still an ongoing topic of study, and we don't exactly know the processes that cause it due to the difficulty in studying it, but scientists are starting to suspect that positively charged particles come from the eruption itself, as well as interactions with ash and the atmosphere. While the island itself was uninhabited, the islands nearby are. Damage from volcanoes comes in many different forms. The most obvious is the ash cloud. The nearby islands around Tonga have been blanketed, with some news reports saying it looks like a grey moonscape on these islands now, covered by a thin blanket of ash. These before and after satellite images are revealing. Residents here were all told to stay indoors while the ash was falling, as breathing it in can be damaging to the lungs. Ash has settled on fresh water supplies, contaminating them. And what was once a green and colourful place now looks like what would happen if you turn the saturation on an image all the way down. This isn't great for plants initially, as it will block the sun's rays from hitting their leaves, although eventually it will be good for the soil of the islands, as volcanic ash is a natural fertilizer containing many important minerals. However, the lightest ash particles didn't just go horizontally across the atmosphere, but they have also certainly penetrated the stratosphere. Typically, the Earth's troposphere and stratosphere don't mix that well, so if ash gets into the stratosphere, it will stay there and circulate around the globe for months to years. The tiniest ash aerosols contain sulfuric acid, hydrogen sulfide, and hydrochloric acid. Interestingly, this may have a very slight cooling effect on the Earth as a whole, as sulfuric acid, for instance, is known to reflect sunlight back into space. However, the negative consequences are that eventually these particles will come back down into the troposphere, where they will return to the surface in rain droplets, or in other words, acid rain. The next thing you'll notice is this incredible shockwave blasting away from the volcano. The fascinating view is best seen in the infrared, as infrared is better at detecting the slight change in atmospheric temperature caused by the pressure wave. The pressure wave travelled faster than the speed of sound, and it was loud. This video may give you some idea of the scale of this shockwave as it passed by an island 65 kilometers away.
Holy sh**.
To be honest, we can be grateful that everyone's eardrums didn't rupture. However, there have been reports that windows from residences were blasted out by the shockwave. This pressure wave is believed to have travelled around the world at least 4 times, as detected by weather stations in various countries. Across the US, the shockwave wasn't audible, but the effects could be seen in the slight fluctuations in air pressure as it passed over the country. However, the shockwave was heard in places as far away as New Zealand and Australia, even in Alaska. Generally speaking, underwater volcanic eruptions don't cause tsunamis, but simply due to the scale and sudden nature of this one explosion, it did in fact cause a tsunami, although not a very big one in the end. It was still enough to do some damage across the Pacific, however, to coastal regions facing the eruption. When news that a tsunami was possible, boats and ships were put out to sea to face the wave head-on. As tsunamis reach shore, the amplitude of the wave increases, causing it to look much more visible compared to a tsunami far out at sea, which is why the wave looks so big here. These boats are not too far from shore. The last damage I want to examine is to the volcanic island itself. This island is very new. It's only been in existence since 2014. This is because it lies right on the Pacific and Indo-Australian convergent plate boundary, a tectonically active area. Before 2014, it consisted of 2 mostly submerged islands, with the caldera around 150 meters below sea level in between them. It had since erupted, filling the gap, merging the 2 islands. As a result, it has actually been studied by NASA themselves to better understand how water impacts volcanoes, as there are plenty of old volcanoes on Mars that would have also been surrounded by water. Scientists wanted to track the erosion of this newly formed island formed in the ocean to see if there are similarities to the erosion patterns on the literal fields of Martian volcanoes, potentially providing additional evidence that certain Martian volcanoes were once also surrounded by oceans of water. It's also interesting for scientists to be able to tell exactly how analogous planets like Earth and Mars really are, despite their differences. As for Hunga Tonga Hunga Haipai, the ash building the island initially was easily washed away by the lapping seawater, like a sandcastle disappearing to the tide. However, after about 6 months, the erosion stopped as the ash and seawater actually combined to produce a harder, more resistant type of rock. And had volcanic activity stopped for good, Hunga Tonga Hunga Haipai would probably have remained a small island for many years to come. However, the force of the January 15th eruption has absolutely decimated the island. What was one stretch of land only last year is now 2 separate islands again, with the caldera disappearing back below the sea level. However, just imagine if one day Earth was to meet a similar fate to Mars and its sea was completely drained. What now looks like a tiny little island to us would still look like a towering 2,000 meter high mountain from the seafloor. While volcanoes on our own planet are pretty intimidating, we can take solace in the fact that an explosion of this size could have been a lot worse for us humans. Moreover, this particular island will continue to be examined by NASA for years yet, helping us understand our own planet, but also our neighbors in the solar system. And why should we care? Well, volcanic activity at this scale can have global impacts, and by studying their interactions with the atmosphere and oceans, we not only can help predict our futures, but understand the past on planets like Mars. Imagine you're at home or at the office when the walls of the room you're in start shaking violently. Books fall off the shelves, cabinets threaten to topple over. You quickly realize this is an earthquake, and then you look up and it occurs to you that there is another entire story of building above you. As the walls continue to wobble, you know that should they fall, that roof above you is coming down and you stand a good chance of dying. So you look up as the quake goes on and you wonder, will it hold? Will it hold? When you see the footage from the Japan 2024 Noto Peninsula earthquake that struck in the afternoon on New Year's Day, when families were gathered in their homes, it's easy to envision the fear that must have been felt by those who experienced it. This was a deadly tragedy, with 241 people killed and 1,296 injured. In spite of its relatively small size, Japan is the country with the 4th largest number of major earthquakes in the world over the last few decades. Our planet Earth is frequently shaken by earthquakes, but there are things about Noto that make it different from any other earthquake that we've seen before. I'm Alex McColgan and you're watching Astrum. And today we'll be entering a world of earthquake swarms and changes to the Earth's rotation. Of earthquake shake tables carrying buildings 10 stories high, and a geological mystery that remains unsolved to this day. It's no wonder that Japan is regularly impacted by earthquakes. Japan sits on the western edge of the Ring of Fire, one of the most tectonically active places on Earth. These vast plates of rock and soil constantly and inexorably shift over the course of millions of years, sometimes pulling apart and sometimes moving together. To further complicate matters, Japan sits along the edge of multiple smaller plates at once. The Pacific Plate pushes west and subducts or slides underneath the Philippine Sea Plate and the Okhotsk Plate. But the Amurian Plate also pushes up against the Okhotsk Plate, while the Philippine Plate subducts underneath the Amurian Plate and the smaller Okinawa Plate at the same time. It's a complex geological wrestling match, one which led to the formation of the islands of Japan in the first place, but one that also causes a lot of friction and tension beneath the surface. What happens when the forces at play become too much for the friction that holds it back and things slip? That's when you get earthquakes. However, in the case of the Japan January 2024 earthquake that struck in the Noto Peninsula, it caught locals by surprise. Why? Because Noto is not actually on one of the major fault lines, and scientists are not yet quite sure why earthquakes are even happening there. If you map out the location of earthquakes by depth and location over the last 25 years, you can see that they congregate mostly on the eastern side of Japan, where the Pacific Plate subducts under the Okhotsk Plate. You can even see how earthquakes that are further west are also triggered deeper beneath the ground, representing the fact that the subducting plate has moved further underground with the additional distance. But rather than striking on the eastern side of the island, the January 2024 earthquake hit Noto to the west. There are other peculiarities. Strange things have been happening beneath Noto over the last 3 years. Since 2020, Noto has been experiencing tens of thousands of small earthquakes in a geological event known as an earthquake swarm. But counterintuitively, this consistent rumbling is normally not something to worry about, as several small shakes are better than one big one, and earthquake swarms generally die out quietly rather than producing large earthquakes. Noto's earthquake swarm bucked the scientific models, lasting too long and producing the exceptionally powerful January 2024 earthquake, and scientists do not really know why. The consequences were serious. The January 2024 earthquake was a magnitude 7.5 and struck at 4 PM Japanese time on New Year's Day, when people were gathered in their homes. It was not just one event, but hit with a number of foreshocks and aftershocks. 1,200 of them that ranged across an area over 150 kilometers across. At least 7 were magnitude 5 or higher. 40,000 homes immediately lost power. Roads cracked. Buildings collapsed. The Japanese government quickly issued a tsunami warning across the west coast of Japan, the first waves of which arrived just 1 minute later in Suzu. A wave as high as 5 meters was expected, although most of the footage captured is a wave of only 1 to 2 meters high. Certainly, the force was enough that buildings along the coast were swept away. All told, there were hundreds of deaths and over 1,000 injuries across 6 prefectures and over $18 billion in property damage. The terrain itself bucked and rose. One strange feature of Noto is that there has been an unexplained upswell that has been taking place there beneath the crust since the earthquake swarm started in 2020. The edge of the peninsula has risen by about 3 centimeters since then, indicating something was gathering down there. Perhaps water? Perhaps magma? Scientists aren't really sure. When the earthquake itself hit, however, that's when the peninsula really started to rise. Some sections of the land rose as much as 4 meters, and you can see the effects in these satellite images. The change in the land's elevation altered where the sea met the shore, pushing the coastline back 250 meters, leaving some ports completely cut off from the water. And when this much land moves, it can influence the rotation of the planet itself. Changing the distribution of mass on the planet's surface changes how quickly it spins. In the same way, a ballerina pulling her arms in will rotate faster. In 2011, the magnitude 9 Tohoku earthquake in Japan shortened Earth's day by 1.8 microseconds, or 1.8 millionths of a second. It's not much, and other effects such as differing sea levels also change the Earth's rotation speed, but it's amazing to see how interconnected the planet is. An earthquake in Japan can affect the entire world. No matter where you are, your life was imperceptibly altered by the Noto earthquake. With all of this, it is no wonder that scientists across the globe are working hard to understand the causes of earthquakes. But for those who live under their constant threat, such as for the people in Japan or other countries like Indonesia, China, or Iran, it's also important to defend against their consequences. So in an effort to improve their architectural design to make them more earthquake resistant, Japan's National Research Institute for Earth Science and Disaster Resilience has taken steps such as developing the world's largest earthquake simulator, eDefense. This 20 to 15 meter shake table supports buildings as tall as 10 stories and can use real-life data to simulate the most devastating earthquakes Japan has ever experienced. By testing different designs in the different types of earthquake scenarios, architects have been able to design braces, beams, and metal joints that reinforce traditional Japanese houses, making them more earthquake resistant. It can be the difference between a building staying upright or collapsing entirely. Interestingly, NASA's space program indirectly helped with creating earthquake-resistant buildings in Japan. Consider the Tokyo Skytree, the world's tallest tower at 634 meters, a place I saw with my own eyes once when I was visiting Japan. Given the risk of earthquakes in Tokyo, it was vital that engineers designed a building that could withstand large shakes. They did so using a central 360-meter tall concrete column that sits on 4 massive rubber bearings, which attaches to the building around it using fluid dampeners developed during the NASA Apollo program. When an earthquake strikes, these fluid dampeners cause the central column to sway at a different rate to the exoskeleton of the building around it. The different rhythms of motion counteract each other, reducing the motion in the building overall. Incredibly, these effects can reduce the force of earthquakes by up to 50%. Earthquakes can carry a terrible cost in lives and destroyed homes and livelihoods. For the Noto Peninsula, the people there have slowly begun the task of rebuilding their lives. Although the broken roads initially made it difficult for emergency services and repair workers to get around, power has been restored to the majority of the 40,000 homes that were affected. Although, as of March 2024, 790 still were without electricity, 18,880 were without water, and 11,400 people were still in evacuation shelters in Ishikawa Prefecture. Earthquakes are overwhelming examples of the natural force that exists beneath us at all times. They can shatter cities, and recovering from them is a slow task. But it speaks to the hardiness and determination of the people who make places like Japan their home. They seek to find solutions to powerful earthquakes to predict them and to mitigate their damage with clever engineering. This can help us all. Through studying the processes that take place beneath our feet, we can better navigate this world that we live on in a way that helps us thrive. The world is dangerous, but also beautiful, and like life, its face is ever changing. It's up to us to face that change until we can overcome any disaster that befalls us. In recent years, researchers have documented a number of weird atmospheric phenomena on Earth that were previously unproven or even unknown. There are transient luminous events like red sprites, blue jets, gigantic jets and elves. There are noctilucent clouds, and rarely seen variants of familiar phenomena like green lightning and red auroras. These are just a few of the incredible occurrences we've been able to observe and verify. Yet, despite amazing advances in our technology and research capabilities, there are still phenomena that are almost completely outside our ability to prove them. Of these, none is stranger and more terrifying than ball lightning, an alleged electrical occurrence so mind-boggling that it sounds, well, made up. Ball lightning has been reported so many times and received so much scientific scrutiny that it occupies an unusual place between science and folklore. But, unlike most myths, ball lightning has a mounting body of evidence that suggests we should not only take its existence seriously, but we might already have proof that it does. So, what is ball lightning? How are scientists attempting to reproduce it in laboratories? And if it is a real phenomenon, as many experts believe, why is it so difficult to prove? I'm Alex McColgan, and you're watching Astrum. Join me today as we look at the fascinating history of ball lightning encounters, examine some of the most intriguing new theories out there, and learn about stunning laboratory experiments that are attempting to get to the bottom of one of science's strangest unsolved mysteries. For centuries, accounts of ball lightning have come from all over the world. The stories vary, but many agree on certain details. The phenomenon appears as a bright burning orb, sometimes golf ball sized and sometimes much larger. It's usually white or blue, but can also be red, orange or yellow. The phenomenon is said to last between 1 and several seconds, float in a slow path, at times changing direction, sometimes even erratically, and has been alleged to pass through walls and windows unscathed. According to some reports, the ball lightning fizzles. In others, it explodes violently, causing severe damage, leaving behind an odor that has been described as sulfurous. At its most destructive, ball lightning has been reported to maim and kill people, and to blast apart heavy walls, doors, and ships. Now, on this channel, we don't accept anecdotal evidence as proof, no matter how compelling. Only observation, controlled testing, and repeatability can confirm a phenomenon scientifically. So, with that in mind, let's look at a few of the alleged ball lightning encounters I find most intriguing. In 1739, the Catherine and Mary were sailing down the Gulf Coast of Florida when it ran into a deadly thunderstorm. According to an eyewitness, a large ball of fire fell from the element and split our mast in 10,000 pieces, killed one man, another had his hand carried off, and had it not been for the violent rains, our sails would have been a blast of fire. That's quite a story, but it gets weirder. In 1753, Georg Richmann, a renowned professor and electrical researcher, was attending a conference in St. Petersburg when he saw a storm approaching. Bringing an engraver to record his observations, he hurried to conduct a kite experiment like the one Benjamin Franklin had performed the previous year. As reported afterwards by the engraver, Richmann was conducting the experiment when a fiery blue orb crawled down the string, fatally striking him and knocking the engraver unconscious. The reported autopsy found a coin-sized red mark on the professor's forehead and injuries consistent with electrocution. But maybe the most compelling eyewitness account comes from 1963, when R.C. Jennison, a researcher at the University of Kent, was flying late at night from New York to Washington. Jennison was sitting in the cabin shortly after midnight when the plane became enveloped in a bright electrical discharge. Within seconds, a bright glowing sphere about 20 centimeters in diameter emerged from the pilot's cabin and traveled the length of the aircraft. In 1969, Jennison published his observations in precise detail in the pages of Nature magazine. Due to credible reports like Jennison's, scientists have taken the phenomenon seriously and put forward numerous models to explain it. One theory proposes that ball lightning could be a hallucination triggered by the magnetic field close to a lightning strike. Citing similar hallucinations experienced during epileptic seizures, this theory suggests that ball lightning could be a figment of the stimulated occipital lobe. However, if true, it would seemingly contradict reported damages caused by ball lightning, such as the death of Georg Richmann. Another hypothesis proposes that ball lightning is a contained plasma reaction, like St. Elmo's fire, the phenomenon famously observed on the masts of ships, when the voltage between the air and the ground is great enough to break the air molecules into highly excited particles. According to this theory, the plasma in ball lightning becomes a self-contained bubble that behaves as a soliton, a self-reinforced wave that maintains its shape and moves at constant velocity. Don't worry if you find this confusing. We're touching on a pretty complicated subject that even researchers are still struggling to understand. One of the most promising hypotheses was proposed by John Abrahamson and James Dinnis at the University of Canterbury, Christchurch in the year 2000. This model proposes that a powerful positive lightning strike can vaporize molecules in soil, causing energized nanoparticles that then react with oxygen in the air to produce light and heat. And remarkably, this model is supported by a strange incident that occurred 10 years ago in Lanzhou, China. Remember when I said that there weren't any verified recordings of ball lightning? Well, that may not be entirely true. In July 2012, researchers from Northwest Normal University had set up spectrometers to record ordinary lightning when a powerful lightning strike produced a glowing white orb. The orb had an estimated glow 5 meters across, which turned red as it traveled for 10 meters before ascending into the air. All this was recorded with high-speed video, which sadly hasn't been made public, and the spectrometer reading, which has. The spectrometer confirmed emission lines from silicon, calcium, and iron, all common in soil. So, if this observed phenomenon was in fact ball lightning, as it appears, then it adds strong evidence to support the vaporized silicon hypothesis. But the model doesn't account for certain behaviors described in ball lightning encounters, such as the ability to pass through solid matter. So what does this mean? Well, either those accounts are wrong, or ball lightning could actually be a collection of separate phenomena. In addition to proposing theoretical models, scientists have attempted to reproduce ball lightning in laboratories with incredible results. One experiment at the Max Planck Institute reported producing a ball lightning type effect when researchers discharged a high voltage capacitor into liquid water. In 2006, researchers at Tel Aviv University conducted an experiment by pointing a microwave drill made up of a magnetron and a microwave beam at a strip of solid silicon. When the researchers pulled the beam away, the drag produced a tiny ball of plasma, nearly identical in appearance to reports of ball lightning. An astonishing result, to be sure, but is this laboratory-produced phenomenon the same as the ones reported in nature? It's very possible, but as of right now, we simply don't know. Another experiment, conducted in 2018, came to even more stunning conclusions. Using advanced experimental engineering, physicists successfully created a Shankar skyrimion, a quasi-particle that is like a tangled three-dimensional magnetic field. Without getting too complicated, what the researchers did was apply an external magnetic field to a system of rubidium atoms near absolute zero. The magnetic field controlled the atoms in such a way that they all spun facing the same direction on the knot surface, while twisting unusually on the inside. In other words, the magnetic field maintained a stable spherical configuration, able to do things like squish or deform while still retaining its essential properties. This discovery could have major implications for quantum computing, but researchers also believe the synthetic magnetic field they created models the expected electromagnetic field of ball lightning. This theory will require a lot of follow-up research, but it's a promising discovery that could explain some of ball lightning's alleged characteristics, such as the ability to pass through solid barriers. So there we have it, a survey of the incredible history of ball lightning encounters, as well as the cutting-edge research that has come tantalizingly close to proving it. So what do you think? Do you find any of these theories convincing? Have you, or anyone you know, ever experienced an encounter with something that looked like ball lightning? I'd love to hear about it in the comments. All the best, and see you next time. Australia has always been known for being a hot place. But when you combine record-breaking temperatures with a prolonged drought, this is what you are left with. A monster wildfire with a smoke trail that stretches for thousands of kilometers, easily visible from the Himawari satellite in space. I'm Alex McColgan and you're watching Astrum, and together we will see how this fire developed from the 30th of December to the 3rd of January, and explore what impact it's had on Australia and the surrounding regions. Australia's climate has always been predominantly hot, with a large portion of the continent being classified as desert. However, the more east you go, the more Australia tends to get wetter due to the mountain chain pushing humid air higher. This means the east of Australia tends to have a more temperate climate. However, in November of 2019, severe drought meant that even the vegetation in these wetter areas was completely dried out, exposing the area to heightened risk of fires. As a result, catastrophic fire warnings were in place around 7 regions of Australia, including the Greater Sydney area. Fires had been burning in Australia unusually early already, and by November, the fires had burned more hectares than the Californian and Amazonian wildfires combined. By late December, the drought hadn't let up, and Australia was about to face one of the most extreme heat waves it had ever experienced since records began, with average temperatures exceeding 41 degrees Celsius across the continent. Under such conditions, fires can occur naturally, and the phrase "spread like wildfire" really holds sway here. This is how it unfolded. On the 30th of December, smoke from the fires can already be seen from space. Their telltale brown hue separates them from the water vapor clouds alongside them. The fire burns throughout the night. And come the morning, there is already a noticeable increase in their size. It was on this day that the military was deployed to some cut-off regions to assist the evacuation of trapped civilians. The smoke trail now reaches across the Pacific Ocean for at least 1,000 kilometers. Fires continue to burn through the night. And in the morning, it's clear that the wind has shifted, and it's taken the smoke in a more easterly direction, completely blanketing neighbouring New Zealand. For some reference, Sydney is around here, and is also completely covered by smoke. This reduces visibility greatly, but also reduces the quality of air for people breathing. Sydney had the worst air quality out of any city on Earth during this time. The final day of this time-lapse really shows the global effect of such an event. On this day, the fires are still burning, and the smoke from 4 days ago is still visible in the air even after dispersing somewhat. The smoke trail is now thousands of kilometers long. The fires have died somewhat for now, due to torrential rain finally falling. However, risks of more fires like these have been forecast in the not too distant future unless more rain falls. Wildfires are indeed a natural occurrence in Australia, however none have been seen on this scale ever. In total, over this season so far, 10.7 million hectares of land was burnt. Putting aside the human, biological and political impacts these fires have had, as that goes somewhat outside the scope of this channel, what is most interesting to me are the weather systems that formed in this smoke. Most people are aware of cumulonimbus clouds, giant thunderstorm clouds that form from water vapor. With the presence of such dense smoke, pyrocumulonimbus clouds have formed, complete with their own thunder and lightning. If you thought regular storm clouds were imposing, pyrocumulonimbus clouds have such an eerie feel to them. Also seen were fire tornadoes, tornadoes formed from heat and air rapidly rising. Another impact from fires of this magnitude are the increased levels of particulates and gases released into the atmosphere, such as carbon dioxide and carbon monoxide. NASA's Aqua satellite has released data showing the carbon monoxide particles escaping the carbon sinks of Australia's forests. Carbon monoxide is extremely toxic to animals and humans, just one of the toxic byproducts of fires. Australia, like many other parts of the world, has always had wildfires, and they always will. The climate is right for such events, and even beneficial in some cases. But what do you think about the ramifications of fires of this magnitude? And have you ever been impacted by wildfires yourself? I'd be interested to hear your thoughts in the comments. Just remember to keep it civil. Imagine for a moment that you're looking out your window when a singular, bright light suddenly flares into existence in the sky above you. This dazzling star is as luminous as the full moon at night, perhaps brighter, and is even visible during the day. If you can see the light, you might already be in trouble, as that unexpected star is now flooding the atmosphere of the Earth with a catastrophic dose of gamma radiation and X-rays, stripping away our ozone layer and exposing us to the full fury of the sun's deadly radiation. And on its way, jettisoned out at 10,000 to 40,000 kilometers per second, a cataclysmic wave of stellar matter and debris hurtles towards our planet. The dying roar of an exploding star venting billions of tons of burning mass at us, ready to sweep across our planet's surface in a tidal wave of fire. This is a supernova. Or at least, it's one interpretation of what we might see if one were to occur near us. But how likely is it for this to actually happen? What constitutes near us on a cosmic scale? How close would a supernova blast have to be before life on Earth would be threatened? What might we on Earth actually experience? And what stars near us have the potential to detonate in this way? I'm Alex McColgan and you're watching Astrum. Join with me today as I discuss an event that could be an Armageddon in our lifetimes, or could be nothing more than a pretty twinkle in the sky. Let's start with the good news. Supernovae in our galaxy are not that common. While astronomers observe hundreds of supernovae every year outside our galaxy, this is mostly a reflection on how many galaxies there are in the universe. Closer to home though, within our own Milky Way, we likely only see about 2 to 3 every century. This means that the odds of one going off tomorrow are not that high. But they're not impossible, and according to archaeologists, the Earth has likely been hit by a supernova before in the course of its 4.5 billion years of existence. For starters, we exist in an area of space known as the local bubble, a relatively sparsely populated region of interstellar space about 1,000 light years across that is thought to have been carved out by a supernova detonation 10 to 20 million years ago, which our planet would have been around for. I talk about that in another of my videos, which you can see here. Scientists have found evidence of another detonation that happened 2.5 million years ago due to a high concentration of iron-60 and manganese-53 in a particular layer of the geological record. This supernova happened far enough away to be harmless to us, but this might not always be the case. There are some scientists who believe that the extinction of woolly mammoths was caused by a massive piece of debris from a supernova crashing into the planet about 13,000 years ago. The impact site in question had magnetic spherules and radioactive potassium-40, a substance found in supernova ejecta. A smoking gun in the era most mammoths went extinct. Even before that, mammoth tusks from 34,000 years ago were found containing tiny impact craters from grains of slightly radioactive iron that had been traveling at 10,000 kilometers per second. If you can recall, that was one of the potential speeds supernovae explosions travel at. That can't have been a nice experience for the mammoths in question. An astute observer from this might be able to note an important fact, however. Evidently, if life began on Earth about 3.7 billion years ago, and we faced 3 supernova explosions that have impacted us in the last 20 million years, and life is still largely ticking along, my condolences, woolly mammoths, if you did die out from one of these, then supernovae as a whole can't be quite as destructive as my opening introduction made them out to be. And that's largely true, although it is, of course, a question of proximity. If I'm 1,000 kilometers away from a nuke going off, I have little to fear. But it's a different story if one detonates on my coffee table. And when it comes to supernovae, it turns out that the universe has relatively large coffee tables. To understand the scale of these explosions, it's necessary to understand the forces involved, which means we need to understand a little better about how supernovae happen. It turns out that there's 2 main paths stars can take to get to that explosive grand finale, although in each case it has to be the right kind of star. For the first path, resulting in a Type 1a supernova, it usually needs to be a white dwarf in a binary system that's gradually or speedily siphoning matter away from its neighbouring star until it reaches a point of critical mass. This path is not fully understood, but it's thought that a white dwarf, or a dense star comprising of mostly carbon in a giant superdiamond core, is normally finely balanced between 2 powerful opposing forces: electron degeneracy pressure and gravity. This simply means that atoms usually object to being squashed too much. Their electrons like to remain at certain distances from the nucleus of the atom and will resist being pushed denser than this point. But gravity is an incredibly powerful force that seeks to draw matter closer, particularly in a dense mass like a white dwarf, where a section the size of a sugar cube has the mass of around a car. And in a binary system where the white dwarf is absorbing more and more matter from its neighbouring star, eventually gravity overwhelms electron degeneracy pressure and the whole house of cards collapses at once. Carbon fusion begins. Within a few seconds, most of the star undergoes fusion, forming into heavier elements and releasing a whole lot of energy as the matter in the star settles into its slightly more efficient new configuration. How much energy? Around 1 quattuorticillion joules. That's 1 followed by 45 zeros. if you claim you knew that number before, you're almost certainly a liar. All of this energy is released in just a few seconds. So naturally, the star ejects its entire contents out in all directions, sending it traveling at 6% the speed of light and unleashing a flood of mostly gamma radiation out across the galaxy. The brightness of this event is 5 billion times brighter than our Sun and burns for a few weeks until the ejector has traveled far enough that the overall energy level has started to dissipate. The second type of supernova, Type 2, is similar, except instead of involving a white dwarf, it involves a massive star at least 5 times more massive than the Sun at the end of its lifetime. These stars are still burning brightly, and rather than just electron degeneracy pressure, it's also the heat of fusion that keeps the star in balance. However, just like a Type 1a supernova, eventually balance collapses. This time is because the star runs out of fuel, and without this additional fusion energy pushing the star's mass outwards, electron degeneracy pressure on its own can't cope with the star's weight to similar effect. The only difference is that while some of a massive star will remain, often collapsing down into a neutron star or a black hole, white dwarfs usually vanish completely. Either way, the scale of material and energy released by a supernova is vast. So vast that unsurprisingly, anything immediately next to it is not going to last long. This is an energy powerful enough to rip apart a star. A planet is going to have no chance if it's in the immediate vicinity. Our own Sun, thankfully, will never go supernova as it's not massive enough, but if it did, there is a good chance the Earth would be either partially or completely vaporized, its rocky exterior reaching a boiling point thanks to temperatures 15 times hotter than the surface of our Sun, and being whisked away in the weeks of the supernova's passing. What is surprising, however, is how quickly this first wave of devastation would dissipate with distance. Indeed, vaporization is realistically not the largest threat a supernova poses. In 2011, experts from the University of Cambridge calculated that even planets orbiting their star at a distance of 15 billion kilometers, or about 100 times the distance between the Sun and the Earth, would remain intact and would instead simply be sent flying out into space now that there was nothing much left to orbit. Of course, such a planet's hypothetical ecosystem would probably have different problems to worry about. Things would get very cold very quickly. Of course, even if the crust of a planet itself remained intact, that doesn't mean that life on said planet would be sustainable. Ignoring the light of a supernova outperforming the brightness of an entire galaxy sometimes, leading to blindness for anyone who saw it, simply stripping away our atmosphere would carry problems. High levels of radiation, even if it didn't affect us directly, would alter the chemical composition of our atmosphere, negating our ozone layer, vastly increasing our odds of dying of radiation poisoning, and killing off phytoplankton in the ocean, and causing mass extinctions as the consequences of that worked its way up the food chain. Scientists put this kill zone to be within 25 light years. Beyond that, the fury of a supernova begins to calm, as distance causes it to wear itself out. Although admittedly the asteroid that potentially killed the mammoths came from a supernova that was 250 light years away, if it happened at all, it was likely bad luck. Generally speaking, we wouldn't notice any damage from a supernova this far away. Its radiation levels wouldn't be high enough to cause mass extinctions. By 500 light years, we'd hardly notice the event at all, other than perhaps seeing a brighter star in the sky. Which leaves one important question. Within 300 light years, are there any supernova candidates we need to worry about? Thankfully, scientists are fairly confident that the answer is no. Massive stars are very noticeable, and the only two that are at risk of going supernova are Betelgeuse and Antares. Both of those are more than 400 light years away. White dwarfs are a little trickier thanks to their diminished brightness. They've been conventionally hard to spot, making it harder to predict whether we might be at risk from them. However, in 2013, ESA's Gaia Space Observatory released a massive packet of information in its efforts to map the stars that allowed scientists to identify 13,000 white dwarf stars within 326 light-years of us. Thankfully, in spite of this large number, scientists remain confident that none of these are scheduled to explode anytime soon. Soon meaning within the next few 100,000 years. Speaking of Betelgeuse, there are some scientists who predict that this red giant might detonate much sooner than that, perhaps within the next few decades. Their research works under the assumption that Betelgeuse has a much larger radius than previously predicted, but if it's true, it might mean that we would get to see a local supernova within our lifetimes. Of course, according to some models, we would have nothing to worry about. The shockwave travelling out from Betelgeuse would take some time to get to us, and even once it arrived, it would be travelling with less force than the push of the solar wind. In other words, it wouldn't be our magnetosphere or atmosphere that kept us safe. The protective sheath of the sun's heliosphere would be enough to keep such a supernova at bay. So, there you have it. While supernovae are perhaps some of the largest explosions in the universe, through some fortunate stroke of luck, our patch of galaxy has nothing really to fear from them. The odds of us being hit by even the neighbouring stars like Betelgeuse that are scheduled to go supernova are incredibly small. True, Earth has plenty of cataclysms of its own, such as floods, earthquakes and hurricanes that can bring devastation to a community in a heartbeat, and space is still a dangerous place. But it's nice to know that of all the things we have to worry about, we can probably cross planetary annihilation from supernovae off our list. The news over the last few weeks have been constantly talking about the heat waves and wildfires across the world. Temperature records around the globe have been broken, from the USA to the Middle East, to Africa, to Japan. Along with this have followed the deaths of thousands of often vulnerable people who couldn't escape the heat. Scientists disagree about whether this summer's heat is due to the effects of global warming, but the impact of this heatwave on the world's carbon dioxide levels are indisputable. I'm Alex McColgan and you're watching Astrum, and today I'm going to take you through what makes the wildfires worldwide so disastrous for our climate, according to NASA research. Firstly though, I'm going to take you through some global warming terms to give you some context for this video. The sun warms the Earth's surface through electromagnetic radiation, similarly to what warms your skin when you're in direct sunlight. This energy is stored by the surface of Earth and then released as infrared radiation, a portion of which goes back towards space. You've probably heard of greenhouse gases. They are gases which basically absorb some of the infrared radiation in the atmosphere, which then warms the atmosphere up. The main greenhouse gases are carbon dioxide, methane, ozone, and even water vapor. Water vapor actually contributes up to 72% of the greenhouse effect on Earth. That's why on a cloudy day, it can still feel quite warm. The greenhouse gas which is in the news a lot is carbon dioxide, and this is because humans are really good at producing it, and we have the greatest influence on the amount of it in our atmosphere. Do greenhouse gases actually heat the atmosphere up though? Well, this is where we can look to space to gain a better understanding, which is one of the reasons why space exploration is so valuable to us. You don't need to look further than our sister planet Venus to see a greenhouse gas's full effect. Venus's atmosphere consists of 96% carbon dioxide, which pushes the temperature across the planet to 462 degrees Celsius on average. That is even hotter than the day side of Mercury, which is much closer to the Sun than Venus. Mercury's temperature on its night side even drops to minus 190 degrees Celsius when it's not exposed to the Sun, because it has no atmosphere to retain the heat. On the other hand, Venus's night side is just as hot as its day side. This is the result of a runaway greenhouse effect. It is thought that Venus could have had a much nicer atmosphere billions of years ago, and even had liquid water on its surface. But as the sun brightened, the planet got hotter, and the surface water evaporated into the atmosphere, causing a greenhouse effect which warmed the planet further, the cycle of which continued until its liquid water ocean boiled away into its atmosphere. This water vapor has since been lost to space, as Venus has no magnetic field to protect the upper atmosphere from solar winds. The H2O rises through convection to the upper reaches of Venus's atmosphere, where UV light interacts with it. This interaction breaks up the water vapor into hydrogen and oxygen. The hydrogen is stripped away into space, with the heavier oxygen recombining into carbon and sulfur oxides. 4 billion years later, it is full of CO2, which was also fueled potentially by the volcanoes on its surface. Even on Earth, the temperature worldwide would be minus 18 degrees Celsius if there was no greenhouse gases in its atmosphere. So they are in fact a crucial part of our existence. However, the balance of these greenhouse gases is critical for our long-term survival. And have these gases stayed balanced? No. This is a simulation of the data from the NASA Aqua spacecraft that shows the increase of atmospheric CO2 from 2002 to 2016. In 2002, the CO2 concentration was around 375 parts per million, until we reached 2016, where we are already well above 400 parts per million. One scientist, Dr. David Crisp, describes how CO2 levels have increased by 20% since he was born, with CO2 already accounting for around 25% of the greenhouse effect on Earth, and with CO2 emissions not looking set to slow down, how high is this number going to be before it stabilizes? Already we are seeing a level that has not been seen on Earth for an estimated 500,000 years or more. But surely the Earth has some natural countermeasures in place, unlike Venus. Well, in fact it does. Carbon dioxide sinks exist, and they are mainly the Earth's oceans and the forests. Earth has an awful lot more carbon than what exists in the atmosphere, but the majority of it is stored in either the ground, in the deep oceans, or in biomass, which includes trees, phytoplankton, plants and animals. Let's have a look at forests in action. Over the course of 1 year in 2006, a supercomputer model was able to see the main contributors to CO2 production, which tends to be big cities. During the winter, trees in the northern hemisphere are not undergoing photosynthesis, which means carbon dioxide is not being pulled out of the air as much. By summer, the levels decrease again as the trees start to pull CO2 out of the atmosphere into a kind of carbon reservoir. Although oceans and trees throughout the year only absorb half the CO2 produced by burning fossil fuels and biomass throughout the year, all of which produce CO2 as a byproduct. However, by the time winter comes around again and the deciduous trees shed their leaves, CO2 levels rise once more, a little bit higher than the average for the previous year. As I mentioned, the other big carbon sink is the world's oceans. The oceans absorb about 25% of the carbon dioxide produced by humans through carbon dioxide from the air dissolving into the water. One of the ways CO2 is used in the water is by phytoplankton, microscopic ocean plants that use photosynthesis to grow. They absorb carbon dioxide out of the water and emit oxygen, and when they die, they sink to the bottom of the ocean, where a lot of the world's carbon is stored. It is not known why, but phytoplankton numbers have also been decreasing year on year, at about 1% per year. This is not good for the overall health of the oceans, as they are the first step on the food chain, feeding everything else in the ocean, directly or indirectly. But that could be a whole different topic by itself. So, CO2 levels are going up. What does that mean for us? Well, some consequences of a warming world are ice caps melting. Snow is great at reflecting heat from the sun back into space due to its bright white color. Smaller ice caps mean smaller amounts of light being reflected back, and instead the heat is absorbed into the oceans, further warming the planet. With the oceans warming up, this can cause more extremes in weather, including hurricanes and drought. As oceans warm up, circulation in the oceans may slow down, preventing it from being able to absorb as much heat and especially carbon dioxide from the atmosphere as the surface becomes less soluble. In 2009, it had already been reported that the South Indian Ocean is up to 10 times less efficient at absorbing CO2 than previously estimated due to a high saturation of CO2 at the surface. Currently, the oceans are still a sink of O2, but the worry is that they could become a source of it instead at some point in the future. Another consequence of rising CO2 levels are that average temperatures worldwide are increasing. Let's compare temperatures from the 1800s, where records began, all the way until today. From this, it is absolutely clear that the world is warming up. Closer to today, 2014 was the hottest year on record. Then, 2016 was the hottest year on record. 2017 almost continued the trend by being the second hottest year on record. And 2018 might become the hottest year on record again, and is currently breaking individual records worldwide for the hottest temperature ever recorded. And here is the crux of the video. A big consequence to climate change is the forests. Vegetation is drying out around the world because of drought and heat. This means it is more susceptible to fire. There is a biome on Earth called taiga or boreal, a region that stretches across Canada and Russia. It is the second largest biome on Earth after the oceans and consists mainly of coniferous forests. In 2014, a fire ripped across a section of boreal forest in Canada's Northwest Territories, the size of Maryland, or 7 million acres. These fires alone released 94.3 teragrams of carbon into the atmosphere, about 103 million tons. This meant that this fire released half as much carbon back into the atmosphere as all the plants and trees in Canada typically absorb in an entire year. Biomass burning currently accounts for 30% of total carbon dioxide production across the world. But the Arctic is warming faster than any region on Earth, and these fires may increase in number and intensity. In 2016, 8.6 million acres burned in the Russian taiga. And on a direct level, let's not forget about the wildfires that recently happened in Greece, the US, and other places worldwide which have directly brought tragedy to people. The issue with these trees burning is that they release a lot of the carbon they absorbed back into the atmosphere. That land will also take a while to regrow, as trees take decades to reach maturity. While these forests are regrowing, they are not the same capacity they once were. In 1988, a wildfire swept across much of Yellowstone National Park, damaging 36% of the park. Less than 30% of the burned area regained forest cover by 2008. Fires aren't the only worry to forests. An increase in natural disasters will also release CO2 into the atmosphere. Hurricane Hugo in 1990 disturbed a huge 4.5 million acre section of forest. This released a large amount of CO2 into the atmosphere as the trees decomposed. There is a slight silver lining though to the increase in CO2. The Earth is getting greener. More of the Earth is covered by vegetation than it ever was in recorded history. The tundra biome is getting warmer, and the increased CO2 levels are giving plants a boost. As a result, more trees and shrubs are growing there. However, this boost may only be short-lived. Studies have shown that plants adjust to increasing concentrations of carbon dioxide, and the powerful boost given to vegetation growth decreases over time. There is no doubt that CO2 and other greenhouse gases are increasing in quantity in the atmosphere. There is no doubt that the average temperature each year is also going up. This video doesn't attempt to solve these problems. I made it simply to raise awareness of some of the consequences to global warming that may even speed up this disastrous process. I must admit my motivation to make this video was driven by the recent news stories of heat waves and wildfires, and I just felt like global warming, was related to these disasters. After researching, I've come to the conclusion that it is. However, you should be aware that there are lots of processes that affect our climate, and I have focused mainly today on the carbon cycle. This is a huge topic, but hopefully I can spark a conversation. The Sun is a giant, bright celestial object of intense nuclear energy. It unleashes billions of tons of electromagnetically charged plasma hurtling into space every day. These violent eruptions, called coronal mass ejections, or CMEs, shoot off into the solar system, causing what we know as solar storms. These highly charged plasma particles race towards Earth at over 1 million kilometers an hour. And one might think that with the speed and intensity of these particles, we should all head for the bunkers when they arrive. However, the Earth has natural protections in place to prevent most of these particles from hitting us. One such protection is the Earth's powerful magnetic field, which pushes the particles around the planet and to its poles. Particles that do hit the atmosphere are absorbed and provide the energy to drive the climate on our planet. In fact, the Sun is crucial to life on Earth. For example, it provides just the right amount of warmth and light so that plants can photosynthesize the Sun's energy to usable carbohydrates. This energy makes its way down the food chain until it reaches us, humans. We eat and convert food to give us energy that our bodies can use. Almost all food energy can be traced back to the Sun, our life giver, and the very beginning of our food chain. But could the solar system's giant also create catastrophe? How big can these CMEs get? What if the largest solar storm of all time was to hit Earth tomorrow? Could the Sun actually damage or destroy humanity? For a star, our Sun is relatively stable, a type of star informally known as a yellow dwarf. It is middle-aged and has not changed dramatically for the last 4 billion years. We can be glad our Sun is as stable as it is, as unlike most other stars, the energy it emits is fairly constant. If you were to look at footage of the Sun taken by the Solar Dynamics Observatory, however, you would quickly realize that even one of the most stable types of star has a landscape of activity. Sunspots, solar flares, and coronal loops are present every single day on the Sun's surface. Could say the surface almost appears to be fluid, but the Sun is neither solid, liquid, or gas. It is rather a giant, nearly perfect sphere of plasma. It is composed of mainly hydrogen and helium, and at the center of the Sun, due to its enormous mass, nuclear fusion takes place. At the Sun's core, hydrogen atoms are fused together under immense pressure to become helium.
The Sun itself, I tend to think of it as an onion. basically consisting of different layers. So in the core, in the very center of the sun, essentially that's where nuclear fusion happens. Now you have to think, so essentially the sun is kind of a huge ball of plasma, soup of particles, ions, atoms, electrons, sort of everything mixed up together. On average, it takes a photon to travel through the radiative zone something like 170,000 years. It's basically it's that dense.
And then from that, it then hits the convective zone. So everybody knows that hot air rises and cold air falls. So what then happens is the material is very hot at the bottom near that radiative zone, and then it expands and it rises to the surface, and that's the main transfer of heat from that point onwards. Obviously then glowing from the surface, like any hotter material does.
Plasma is an extremely good conductor of electricity and is also affected strongly by magnetic fields.
So sunspots are actually the surface representation of the magnetic fields of the sun. So the magnetic fields actually get very tangled below the surface. So between that radiative zone and the convective zone, the magnetic fields get tangled.
They tend to appear in pairs, in groups. If you think sort of a magnet, you have positive polarity, negative polarity. That's sort of normally what we see in sort of in sunspot pair. One would be positive, the other would be negative. And normally sort of the strongest magnetic fields that we observe are in the sunspots.
The sunspots can be anywhere from about 15 kilometers in size to around about 160,000 kilometers, so multiple times the size of the Earth.
Sunspots can often be seen at the base of various solar phenomena. Coronal loops, large rings in the sun's atmosphere, prominences, large, bright, gaseous features extending outward from the sun's surface, reaching into space for thousands of kilometers. And solar flares, a sharp increase in the sun's brightness and temperature.
Solar flares tend to happen over active regions, and active regions are essentially sunspot groups. So these are the locations where we definitely see the strongest flares.
So a reconnection event is essentially what produces the energy that causes both flares and CMEs.
Because the convective zone is very turbulent, many of the sort of current simulations show that most of the magnetic field, as it rises through the convective zone, is being destroyed, being diffused around. It's more complicated magnetic structures, such like twisted magnetic fields, that tend to survive. And so you can imagine, especially sort of over large sunspot groups, we do see very complex magnetic field configurations, magnetic fields, twisted, wreathed, basically creating these complicated geometrical topological structures. And it's within that structures that magnetic fields, the magnetic energy is stored. And what happens during reconnection? I tend to describe it, think of the magnetic field as a rubber band. So you twist it, turn it, and then basically at some point you pull it too strongly and it breaks. And that's essentially when we have the reconnection event. And what happens during the reconnection event? Essentially, as the name suggests, the magnetic field lines reconnect.
And when that happens, you get a lot of energy being released. Of the order of millions of nuclear weapons, nuclear bombs, all in one instant. And that energy will produce both solar flares, where large amounts of radiation is released, and also potentially lead to large-scale movement of the material that was suspended in the prominences, both towards the sun and away from the sun. When that reconnection event happens, then again, the material which is suspended in those magnetic fields normally will move one way or the other. A lot of it will move back towards the sun, often following those magnetic field lines, so moving to the footprints, like for instance, move to the sunspots, if that's where the footprints are. But equally, in the middle of those magnetic fields, quite often a bubble of material is essentially ejected away from the sun. And so what you'll end up having is millions of tons of charged material flying out from the sun relatively fast. I mean, of the order of hundreds of kilometers per second to thousands of kilometers per second. And those are what we call CMEs, coronal mass ejections.
These CMEs come in contact with the planets all the time. Venus, when faced with a CME, has its lighter particles stripped away in the higher reaches of the atmosphere by the force of the ejection. This leaves the planet with just the heavier molecules, a toxic smog that cannot, as far as we know, sustain any life. Earth would have a similar fate if it wasn't for its relatively strong magnetic field. Particles from a CME aimed at Earth are redirected around the planet because of the Earth's magnetosphere. Some particles get redirected to the Earth's poles, where the charged particles hit the Earth's ionosphere, causing beautiful aurora. Thanks to a combination of the Earth's magnetosphere and atmosphere, we are totally protected from all sorts of particles space likes to throw around. Or are we? When the Earth is hit by a CME, this is called a geomagnetic or a solar storm. When a solar storm hits us, Earth's magnetic field gets somewhat compressed by the force of the CME for the duration of the storm. Normally this wouldn't and hasn't been a problem for people with their feet firmly on land. But what would happen if the most powerful solar storm ever recorded was to hit Earth today? To find out what is believed to be the most powerful CME in recorded history, we have to go back to 1859 to a solar storm known as the Carrington event. From the 28th of August to the 2nd of September 1859, many sunspots appeared on the sun in one place. On the 29th of August, southern aurora were visible as far south as Queensland, Australia, which implies a solar storm was occurring. Before midday on the 1st of September, amateur astronomers Richard Carrington, who the event was named after, and Richard Hodgson separately saw and recorded an extremely bright solar flare. Carrington and Hodgson wrote reports independently, which were both later published in scientific journals. The flare was connected to a major coronal mass ejection that travelled directly towards Earth, taking 17.6 hours to make the 150 million kilometer journey, much faster than the speed of normal CMEs. Typically, a CME would take several days to reach Earth. It's thought that the high speed of this one was made possible by a prior CME, perhaps the cause of the large aurora event on the 29th of August in Australia, which would have cleared any ambient solar wind plasma for the Carrington event like a giant slipstream. With this slipstream in place, the way was set for the biggest CME known to man. On the 1st to the 2nd of September 1859, the largest recorded geomagnetic storm occurred. Aurora was seen around the world, all across the northern hemisphere, as far south as the Caribbean. The aurora over the Rocky Mountains in the US was so bright that the green glow woke local gold miners, who began making breakfast as they believed it was morning. It was reported that because the aurora was so bright, people in the northeastern United States could still read a newspaper. The aurora was visible as far from the poles as Sub-Saharan Africa, Mexico, Queensland, Cuba, Hawaii, and even at lower latitudes very close to the equator, such as in Colombia. This is unprecedented, as typically aurora aren't visible at the middle latitudes. By the 3rd of September, the aurora in the sky was said to be the brightest and most brilliant it had ever been. However, although beautiful, this storm brought unforeseen problems. A consequence of the geomagnetic storm was that the electrically charged particles from the sun surged telegraph systems all over Europe and North America, which caused them to fail, even in some cases giving the people that operated the telegraph equipment electric shocks. Telegraph pylons threw sparks from the charged atmosphere. Amazingly, some telegraph operators could still continue to send and receive messages even though they had disconnected their power supplies. The storm was comparable to a hemisphere-wide EMP bomb, fairly harmless to humans, but extremely bad for electronics. The force of the CME in 1859 was so strong that it compressed the magnetic field of Earth all the way down to its atmosphere. Due to the fact that North America and Europe were facing the sun at the time, these areas of the world were most affected from the initial cannonball of the CME. Looking back at geomagnetic storms since the 1850s, there have been a few which were big but not devastating. For example, in March 1989, a CME hit Earth, rendering satellites unusable for several hours and jamming radio stations in Europe. Power in Quebec was knocked out for about a day. Some people there incorrectly thought the Soviets were attacking, and the glow in the sky was the result of nuclear bombs. Thankfully though, this solar storm and many like it did no lasting permanent damage. Today, if a CME the size of the Carrington event or bigger was to hit Earth, the consequences would be far more disastrous than they were for mankind in the 1800s. Technology was only just picking up back then, whereas today we have satellites in space, computers, telecommunications, power plants that would all be severely damaged in such an event. Due to the range of a solar storm, it would greatly impact equipment over a large area, the most susceptible technologies being the electricity grid and telecommunications, which have cables stretched out over a large distance. Without proper safeguards in place, transformers on the power grid could break, and millions upon millions would be without power for a lengthy period of time. If transformers did get damaged, for example, it would take years to replace, as transformers take years to manufacture. Often, these transformers are tailor-made for the specific requirement and are not mass-produced. Without power, refrigerators would not be able to stop food from spoiling, and as the transport system would also be down as fuel stations require electricity to pump, replacing that food would be problematic. Payment systems that rely on credit cards would not work. People would not have access to the internet as computers would not have power, and battery-powered devices would run out quickly. Radio and TV stations would be disrupted. Hospitals would struggle when the backup generators ran out of fuel. We would be completely cut off from the outside world. The world is simply so dependent on technology, and especially on electricity. It is feared we have lost the ability to function as a society without it. And worryingly, it is our power grid that is most vulnerable to a super solar storm. An independent think tank recently put the cost of damages to the USA alone at $2.6 trillion, ultimately destroying the economy. And unfortunately, that does not cover the social impact it would have. As is often the case in natural disasters, some people would undoubtedly resort to more primeval instincts, with attitudes such as every man for himself. Chaos, looting, and disregard for the law could occur. This would only get worse the longer the population goes without hearing from their government or organization of authority. Hopefully, in such a situation, the good of mankind would prevail, but it is a possible scenario. The think tank placed the estimated recovery time to repair the damage of a CME at 4 to 10 years, and estimated that 2/3 of the US population could die of starvation, disease, and chaos during that time. We only need to look at a couple of examples to understand the severity of the situation. In 1989, Quebec experienced a large solar storm that made the power grid fail in just 90 seconds. This problem was exacerbated by the fact it was winter, where the temperature can drop well into the minuses, which left vulnerable people in a potentially bad situation. It took 9 hours to restore power, and total costs from the disruption were estimated to be around 2 billion Canadian dollars. From the social aspect, we only need to look at Puerto Rico, which is still without power for 40% of its population from the time of writing this script in early February. That means it has been without power for 140 days, and is estimated that it still needs 50,000 utility poles and roughly 10,000 kilometers of electricity cables. If a solar storm hits, it wouldn't just be an island that is rendered powerless, it would be an entire hemisphere. And Earth has had some very near misses. A Carrington-size event could have been a reality in 2012, where a huge CME was ejected from the Sun. This was the biggest CME that has been recorded with modern technology, and it directly hit one of the stereo satellites that was observing solar activity. It is the charged particles that cause this distortion effect shortly after this solar flare. And had it hit Earth, the hypothetical disaster scenario could have become a reality. Due to lack of historical evidence, we have no way to predict when the next big CME could hit Earth. As far as we know, a CME even bigger than the Carrington event could hit us tomorrow, or the next one could be in a few thousand years. But what mitigation plans does the world have in case of such an event? Since 1995, NASA have placed a telescope in orbit which is constantly monitoring the Sun for CMEs. As light travels much faster than the speed of a CME, it would roughly give us about 17 hours warning before the CME hit Earth. If everyone was acting fast enough, this might be enough time to turn off some of the power stations, thus protecting the electricity grids. This is called the Solar Shield Program, and astonishingly, the US is currently the only country to have such a program in place. Countries are also working on temporary transformers, which are quicker to produce. Additionally, countries throughout the Western world are currently in the process of proposing upgrades to the power grids that would not allow a surge of electricity caused by a geomagnetic storm to destroy the network. This process, however, is slow and bogged down by bureaucracy. It seems countries are in no rush to foot the bill to upgrade the infrastructure. These measures to protect the power grid are not already in place worldwide. It also seems that most people in the world are not even aware of CMEs. but rather fear much less likely scenarios like an asteroid hitting Earth or aliens invading. Mankind as a whole is shockingly unprepared for a natural disaster caused by a super solar storm. George H. Baker, Professor Emeritus from James Madison University, spoke before the House Committee on National Security in the United States and gave this explanation for the reason progress is not getting made. He said, "To a major extent, the lack of progress in protecting our most critical infrastructure to solar storms is that the responsibility is distributed. There is no single point of responsibility to develop and implement a national protection plan. Nobody is in charge." When I asked the North American Electrical Reliability Corporation about EMP protection, they informed me, "We don't do EMP, that's a Department of Defense problem." The Department of Defense tells me EMP protection of the civilian infrastructure is a DHS responsibility. DHS explained to me that the responsibility for the electric power protection is within DOE, since they are the designated sector-specific agency for the energy infrastructure. And this is sadly from one of the most progressive countries in the world on the subject. And until mankind is prepared for a CME, we really are at the mercy of our life-giver star.
Are we the last technologically advanced civilization ever on Earth? It's possible. Humanity has risen to the position of the dominant species on the planet, 8 billion strong. We have planes, cars, robotics, advanced computers, and the capacity to send our spacecraft to distant celestial objects, and soon maybe we will even travel there ourselves. And yet, Rome wasn't built in a day, nor without cost. It has taken billions of tons of coal, oil, and natural gas to fuel the industrial revolutions that have made society into what it is today. Those resources are not infinite, and they will take millions of years to replenish themselves. Which begs an interesting question. Was this a one-time deal? If something were to happen to civilization, if some cataclysm or nuclear holocaust were to send us all technologically back to the Stone Age, or even wipe us out completely, are there enough resources left that some future civilization could rebuild? Or are we now the first and last civilization birthed by our Earth that will ever reach for the stars? And if so, why? I'm Alex McColgan and you're watching Astrum. And today we will explore the rise of our technologically advanced society and learn what materials you need to build what we now have. And then we will discover how much of those vital ingredients are left. But for the sake of this thought experiment, let's start by activating Doomsday right now. Boom! In one fell swoop, humanity has been sent back to the Stone Age. All technology has been annihilated, perhaps in a horrific nuclear exchange. Human society has collapsed. Whoever survived is now tasked with rebuilding civilization in a world with no buildings, no machines, no books, and perhaps worst of all, no internet. Let's say for the sake of this thought experiment that natural resources are unharmed, but nothing can be salvaged from the civilization before. Like the ultimate survival game, everything must be built from scratch. Once our survivors have gotten over the shock of this horrifying turn of events, they will quickly realize that they need at least 3 vital things if they want to live: food, clothing, and shelter. And fortunately, these are all accessible through various renewable sources. These will not be the limiting factors when it comes to restarting civilization. With wood, you have building materials. Wool or cotton can be woven into clothing. Animals, vegetables, and fruit can be hunted and gathered for sustenance. Conveniently, these natural resources can be accessed with some very simple tools. Some sharp sticks for hunting and fishing, and some simple axes and knives for chopping and fashioning wood, made out of nothing more than sharp stones tied to sticks with hempen rope. With this at its base, a civilization that develops after us could absolutely and easily reach a thriving hunter-gatherer society. we should even be able to get further than that. Although if our civilization is ever going to get to the stars again, they will need to start by stepping up from stone tools to bronze and iron. For bronze, an alloy made from mixing tin and copper, wood-burning fires will be enough to get by. Metal ores extracted from the ground need to be melted to separate the rock and impurities. Smelting tin requires temperatures of 230 degrees Celsius, and smelting copper needs a little under 1100 degrees Celsius. Fortunately, a large wood-based bonfire can reach temperatures of 1100 degrees Celsius, making bronze just about accessible to our new civilization. But it is with iron that the problem comes into a focus. Iron is tricky. While this metal is extremely plentiful in the Earth's crust, its melting point of 1583 degrees Celsius means our fledgling civilization would need to do more than just place it on a wood-based bonfire to be able to smelt it. Fortunately, there are workarounds to this problem. By partially burning wood in low oxygen conditions, you can make charcoal, which burns at a higher temperature than the wood it's formed from due to the fact that the initial combustion cost of getting rid of all that water and sap has already been paid. This can be further enhanced by placing your fire in a kiln and controlling airflows. With the right flow, even a wood-burning fire can reach temperatures of 1500 degrees Celsius, such as with the record-breaking Sunan snake kiln in Taiwan. But using charcoal comes at a cost. You need a lot of forestry if you're going to get enough wood to support a metal-hungry civilization. It will need to be replanted regularly, but more crucially, you won't be able to turn that land into farmland, something your civilization will also need if it wants to grow and develop. This is why most nations use fossil fuels to produce their steel. Coal or methane gas can be used to create incredibly hot fires, without requiring you to give up your farmland. You might be wondering if our new civilization could do without these fossil fuels. If we just grew a little more slowly, with a smaller population, couldn't we make charcoal work? Charcoal is carbon neutral, as the trees that create it grow it by removing carbon from the atmosphere. Couldn't a new civilization reach our level and get to space again without using fossil fuels in their production? The answer is no. The absence of fossil fuels would be devastating to a civilization trying to reach for the stars. This may be an uncomfortable thought, but just consider for a moment the degree to which our own civilization uses coal, oil, and gas. Now, I'm not advocating that we don't need to do better. Just because we currently use a lot of fossil fuels as a species doesn't mean we shouldn't try and reduce and care better for the planet. At the end of the video, I'll talk about Planet Wild, a channel that goes into that in more detail. When we talk about using fossil fuels, it's easy to think about them only in terms of electricity production, which our new civilization would need to get to if it wanted to get back to space travel. In fairness, fossil fuels remain the world's primary energy source. In 2022, 83% of the world's energy came from these sources. But fossil fuels are also incredibly important in the production of 4 other vital ingredients for our civilization. I've already mentioned steel, for which our current global demand sits at 1.8 billion tons a year due to its strength and durability as a building material, but there is also concrete, plastic, ammonia, and silicon. Can you imagine a world without concrete? Without fossil fuels? You would probably have to. The sand and gravel that makes concrete up are easy enough to acquire, but the cement that binds it all together, made from a mixture of limestone and clay, requires temperatures of 1400 degrees Celsius to melt them together properly. If our new civilization wanted to make concrete, which would be useful as it's an extremely malleable, durable building material, useful for building a spaceport for launches and many other buildings and platforms, they would need to find a fuel that could burn at that temperature. The civilization that comes after us would need a lot of charcoal to fill the gap if fossil fuels were no longer on the table. But that's not even an option for silicon. Silicon has widespread use in our society, from ceramics to brickwork, but by far its most influential trait is that, once refined and purified, it's the element used to make computer chips, thanks to its abundance and its properties as a semiconductor. It's extremely easy to find in its raw form, but refining it is a complex process that requires temperatures of 2,350 degrees Celsius. Charcoal does not burn that hot. Not for nothing have the last 100 years been referred to by some as the Silicon Age. Can you imagine our world without computer chips? In terms of getting to space, the computers that guide and control the launch of a rocket would certainly struggle without computer chips. There's more. Ignoring materials that simply need high heat to smelt or refine, fossil fuels are literally a building material we use to make our products and feed our population. While we sometimes express concern about the amount of plastic being used in the world, there's no denying its importance to modern civilization. It makes keyboards, boxes, sterile tubes, and syringes for medical applications, polyester clothing, car bumpers, wind turbines. Yes, even green energy sources like wind turbines are made out of materials that require fossil fuels. A wind turbine is around 70% steel and 10% plastic. Both are fossil fuel reliant. Plastics are also used in rocketry. Having a lightweight material that's easy to mold, fairly rigid, and above all, light, is extremely useful for rockets that are trying to shave every gram of weight off. Launching without plastics makes rockets much heavier, requiring more fuel or smaller payloads. Finally, let's consider ammonia. While you might think we could do without plastic in our lives, without ammonia, it is likely that about half of the Earth's present population would starve to death, which, while not directly related to getting to space, is a bit of a problem on its own. Ammonia is used in fertilizer. Although other natural fertilizers exist, they lack the potency provided by ammonia. Without ammonia, we simply would not be able to sustain the amount of food production that we need to support the global population, not by half. And ammonia is made from methane, which is mainly sourced from natural gases. When viewed through this lens, it's easy to see the scale of the challenge that would be faced by a civilization trying to reach a technological level where they could explore space if they didn't want to or didn't have access to fossil fuels. And let's be honest, the easiest to get to fossil fuels on Earth are now mostly gone. You need serious equipment to get to the fossil fuels we are now extracting, which required fossil fuels in the first place to build. Our civilization has been built on the back of fossil fuels. They provide our plastic, our steel, our concrete for our buildings, and our energy. Without them, we would struggle to produce the metal for a rocket or the fuel that powers it with the computers that guide it. And so, for the sake of our thought experiment, how much fossil fuels have we used? And is there enough left so that the civilization that came after us could do it all again if they really had to? It's difficult to find estimates that accurately lay out how much fossil fuels have been used up by this point. Our current usage is at around 15 billion metric tons per year, although this figure has been climbing for some time, so will likely continue to increase as our population does. However, by projecting our current usage back across the past, and by factoring in the increase in demand over time since 1800s, when the Industrial Revolution roughly began, it's possible to arrive at a ballpark estimate of 750 billion metric tons of fossil fuels consumed by the human race to get to where we are now, by multiplying our current yearly usage by the number of years between 1800 and now, and then approximately quartering the result, to reflect the fact that demand was considerably lower most of that time. Now, we do not know how much fossil fuels we have left. Current estimates based on proven reserves suggest that we will start running out of fossil fuels in just 50 years' time. Coal will last longer. Coal reserves should keep the lights on for up to 130 years, but oil and natural gas could potentially all be used up in the lifetime of people around today. Calculating based on our current usage, this works out to at least another 750 billion tons of fossil fuels remaining, the same amount that got us to this point, only we're currently burning through it much faster. Of course, this number could be much higher. This estimate is based only on proven reserves. If more oil fields are found, or technology is developed that can allow us to access fossil fuels better, the amount of fossil fuels available in the planet could be a lot higher than current estimates. Still, this is enough information to provide us with our answer. A civilization that rises after us would indeed have enough resources to get to the same technological level that we are currently at. But they would likely find it much harder, as much of those untapped fossil fuel reserves are buried at much deeper depths than the ones our own civilization found. We have burned the supplies that were easy to get to. In 1950, the average depth you needed to drill to access oil was 1.1 kilometers. This now stands at 1.8 kilometers, but some oil and gas fields are as deep as 9.1 kilometers. It wouldn't be easy, but the resources are currently there, for now. If we ask this question again in 50 years' time, we might arrive at a different answer. It might be necessary for future civilizations to get used to the idea of a more comfortable, arable existence. Still, if there is a ray of hope to shine on this, it is that necessity is the master of innovation. The materials we use are the most effective at what they do, but that's not to say that with sufficient will, a new civilization that comes after us couldn't get to the stars again even without fossil fuels. They might need to go slower, their population might never reach our levels, and many would have to make do with rougher tools or suboptimal materials. But where there is a will, there is a way. Perhaps a future civilization will one day harvest methane from bio-waste. Methane can be used as rocket fuel. Without fossil fuels, the civilizations that came after us would look very different from our own. They would have different priorities, and would perhaps use their land with a different focus in mind. But perhaps they could get to the stars in their own way. Thanks for watching. We are now very close to our end goal of 1,000 astronauts on Patreon, and I can't thank you enough for having answered the call. The closer we get, the more it's looking like I'll be able to expand our content here and bring back Astrom Answers. So submit your video suggestions and questions over on Patreon. If you'd like to become an astronaut, you can join the Patreon with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Once again, a huge thank you from myself and the whole Astrom team. Meanwhile, click the link to this playlist for more Astrom content. I'll see you next time.